Let's talk about something called the common ion effect, which we can use to describe certain situations in equilibrium. Okay, and so let me first tell you what this common ion effect is. Okay, sounds like this crazy, topic or thing, but it's really nothing more than a specific application of the Chatelier's principle when you're dealing with solutions that have certain ions or species that are in common with other ones. Okay, so let's say that you had some kind of water-soluble salt, like maybe NaCl, and you added that to a solution that contains an insoluble salt, like AgCl, or maybe the solution has a weak acid or a weak base, and that salt that you added, right, the sodium chloride, maybe has an ion in common with the acid or the base or the solid itself. Then what's going to happen is the dissociation is going to be affected by that, okay, because what I'm doing is I'm changing the concentration of one of the products, okay, in the reaction, right? One of these ions is found on the product side of the reaction. So because of that, the equilibrium is going to shift, and the equilibrium is going to have to shift, according to Le Chatelier, to oppose that. So it's going to have to go to the left, right, back to the reactants. And so what's going to happen is, if I do this in a smart way, I can eventually wind up with something called a buffer. Okay, and so you may have heard the word buffer before. Okay, a buffer is really just a special kind of solution that has both things in there. Okay, it's got an acid as well as the salt of its conjugate base, or a base and the salt of its conjugate acid. And so they're both in there at the same time to kind of counteract any external additions of strong acids or strong bases will react with either the acid or the base that's present in the buffer. Okay, and so speaking of which, let's talk a little bit more about this magical world of buffers. Okay, there are different definitions that people use to describe what a buffer is. Okay, if you've taken biology, you may have heard the biological definition of a buffer, which is a solution that resists change in pH, right? Doesn't change the pH. And you say, wow, that's impressive, but how does it do that? Well, to understand how it actually tries to resist changes in pH, we have to look at it, I think, from more of like the chemical perspective. Okay, so the chemical definition of a buffer is a solution that's made out of a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay, so why are these basically saying the same thing? If I had a small amount of a strong acid that I added to the buffer, the strong acid is going to want to react with something basic, and the base is going to be the conjugate base that's found in the buffer. And so there's going to be a neutralization that takes place between the strong acid and the conjugate base in the buffer, and that neutralization is going to basically annihilate this strong acid that got added, so the pH of the solution will not be altered. Or conversely, if I had a strong base, that's going to want to react with the conjugate acid that's present in the buffer. And so those are going to annihilate each other and neutralize. And once again, the pH is not going to change as well. Okay, and so the point is that I will only very slightly change the pH as long as I add a relatively small amount of a strong acid or a strong base. Of course, if I add a tremendous amount of strong acid or strong base, the buffer can't do this forever. Eventually it'll break down and the pH will start to change. So this brings up this notion of a buffer capacity. Okay, the buffer capacity indicates across what range can I add acids or bases and still have a relatively constant pH before things start to be different. Okay, in general, the more concentrated the buffer is, the better it's going to be able to neutralize the incoming acid or base, which makes sense if you think about it, because if you understand how the thing works, right, I need the conjugate acid or the conjugate base to neutralize or annihilate this incoming strong acid or strong base. So the more of it that I have to begin with in the buffer, the more this annihilation can happen, and the more I can kind of resist the effects of these strong acids and strong bases in changing the pH. Okay, so that's number one, right? Buffers work the best when I have pretty high concentrations in the buffer. The other thing is I want to have approximately equal concentrations of the components in the buffer, which means the strong acid, the weak acid and the conjugate base, or the weak base and the conjugate acid. Okay, and so in order to have approximately equal concentrations of the conjugate pair, the acid and the base, typically buffers get prepared so that the pH of the solution is approximately the same as the pKa of whatever that acid is. Okay, and so you want to try to adjust things so that the pH of the solution is close to the pKa of what you're using for the buffer.